So now we're solving this boundary value problem with this unknown parameter in it. Y is a function of x. X goes from 0 to L. So it's a finite extent on the argument x. And again, we want to know what lambdas here give us non-trivial solutions. The trivial solution is the zero solution. Zero, if y equals 0, it satisfies everything here. And we just went through that there's three cases, depending on if lambda is negative, exactly 0, or positive. And these canned solutions for those equations. So let's go through each case. We have three cases. When lambda is less than 0, we had this general solution. So now let's test that general solution against the boundary condition. One condition was if the argument is 0, the answer is 0. So if we put in 0 for x, cosh of 0 is 1. Sinh of 0 is 0. So we just get C1 must equal 0. So what's left as a solution that satisfies that boundary condition is this here, C2 equals sinh alpha x. The other boundary condition is that when x equals L, the answer is also 0. Remember, we were given these boundary conditions. When x is 0 or x is L, y is 0. So we have this condition now. When we put in x equals L, this must equal 0. Sinh of anything that's not 0 is not 0. Let's go back to our quotient sinh. This red line is sinh. It's only 0 exactly at 0. So when the argument is not 0, sinh is not 0. That forces us, that means C2 must be 0, which means we have a trivial solution. So we reject that case. Now about the other case where lambda exactly equals 0. Here was the general solution. Plug in 0 for x, we just get C2, and that has to equal 0. Which leaves us with this solution that satisfies that boundary condition. You put in now L for x, it's C1 times L equals 0. L is not 0. We're assuming this length on x is not 0. L is something greater than 0. And again, we get that forces us to make C1 0, which makes the whole solution the trivial solution. So we reject that case as well. Two of the three cases we reject. What do you think is going to happen with the third case? That's when lambda is greater than 0, which means it equals some positive alpha squared. Here was the general solution in that case. Plug in 0 for x, the cosine is 1, the sine is 0, so we get C1 equals 0, which means here's the surviving solution. Now we'll put in L for x, and we get this must equal 0. Well, the sine of something equals 0 an infinite number of places. Every place the argument is an integer number of pi, the sine is 0. So any alpha times L that equals an n pi, where n's an integer, gives you a non-trivial solution. So we're going to say alpha, we're going to get a bunch of alphas. Should call this alpha sub n actually. Alpha equals n pi over L. So the lambdas are those n pi over L squared. And the solutions then are these signs where that alpha is plugged in there. So here are the non-trivial solutions. And there's an infinite number of them, one for every integer n. Well, we call those lambdas the eigenvalues. So here are the eigenvalues. If I list them, the list would start looking like this. By the way, these have to be positive integers because we said alpha was positive. The solutions themselves, the functions, the sine of n pi x over L, those are called the eigenfunctions. Here's what the set of eigenfunctions would look like. It's an infinite set of functions. So that's a big thing here. Eigenvalues and eigenfunctions. It came about from solving a boundary value problem with this unknown parameter lambda in it. That's the introduction of eigenvalues and eigenvalues. We'll do another example in another recording.